So let's start our class for today. Okay, now we are going to look at the chapter 2. Okay, in the chapter 2, okay, you will learn about the processors. Okay, we have a lot of embedded processors. And then after that, we are going to look at the high level language programming. Okay, which is the language that we are going to use in the embedded system. Okay, usually we are going to use the C programs and the platform. Okay, later the platform for embedded system that we're going to use in this course is Linux. Okay, so first of all, let's look at the objective. Okay, so the objectives of this module are to learn about the processor types and the difference. Okay, so you are going to look at what are the embedded processors. Okay, what are the type of the embedded processors and what are the difference between one processor with another processor. And then you are going to understand the HLL, which is the high level language compilation process. Okay, how to compile, how to do the programmings and so forth. Okay, and to learn about the GCC and Intel C++ compiler to change. Okay, later you will learn about how to use the GCC. Okay, in order, because we are using the Linux environment. Okay, you need to know how to uh, execute your compiler, how to read a file from compiler, and etc. Okay, so there are few processor types, okay, available in the market. Okay, one of them is we call it as a embedded processors. So this embedded processor is a microprocessor that is designed especially for coping with the wishes of an embedded gadget. Okay, so this embedded processor will execute the instructions sequentially. Okay, it has a smallest unit and instruction set which depend on the different architecture. Okay, there are three computer architecture types used in the embedded system. Okay, one we call it as a RISC. Okay, so RISC is actually a reduced instruction set computer. Okay, so this RISC utilize a small, highly optimized set of instruction, which is it will execute one action per instruction. Okay, if for example, if you're going to load data to your register, okay, so you need to have one instruction to do it. Okay, so every instruction will have a one cycle. Okay, or every action will have one instruction. Okay, so by taking just one cycle to complete operation, execution time is optimized. Okay, so that is a RISC. Okay, then we have this. Okay, so the example of RISC is such as the Atmel AVR processors, and then we have the IBM power processors. Okay, then the second architecture is CISC. Okay, which is this one here is a complex instruction set computer. Okay, so since it is a complex, means that single instruction, okay, you have one instruction can execute several low level operation. Okay, for example, okay, such as you're going to load from a memory, so an memory operation and a memory state means that one single instruction can execute a few actions. Okay, compared to RISC, one action. Okay, so this one here, yang ni, one action, one instruction. But for CIC, okay, you have one instruction, but you can have several. Okay, it can execute several actions. Okay, so that is the difference between the CISC and RISC. Okay, so the example of a CISC, such as a Intel x86, and then you have an AMD K5. Okay, so this is an examples lah, okay, of CISC architecture, okay, which is widely used in your computer, all right, in your laptops and etc. And then this is the RISC. Okay, so by using the IRC, this is a examples lah of RISC architecture, which is this. You can see here, this is a Atmega. Okay, this is a Atmega chips lah. Okay, and then the last but not least is the advanced RISC microcontroller, or sometimes we call it as a ARM. Okay, so this ARM here, contoh is Cortex M0 and Cortex AX series. So this is an example of the embedded processor for advanced RISC microcontroller. Okay, and then this embedded processor, okay, can be divided into three varieties. Okay, kita ada tiga varieties. Okay, the first one we call it as a microcontroller. Okay, so this is microcontroller. So you always use the microcontroller. You already learn about the microcontroller. It is a low-cost processor with on-chip I/O device and memory. Can range from 1 to 32 bits size, okay, memory size, okay, and data register size. Okay, so actually this microcontroller, okay, needs to have the, it have a I/O chips and I/O device and memory inside of this chip in order to make its works lah. Okay, so example of a microcontroller such as the microchip PIC, and then we have the Intel 8051 or Motorola 60HC11. Okay, so the example of a Motorola HC11. Okay, and then next, the second one here, we have the embedded controller. Okay, so it's the largest device, okay, which is the size is 16 or 32 bits with include I/O device only. Okay, so inside of here, it have the I/O device or GPIO. Okay, so memory is usually external. Okay, so the memory, you need another chip, okay, to connect with this controller. Okay, so that it make a one complete system. Okay, example of embedded controllers such as ARM, MIPS. Okay, then after that, the last one here is we have the general purpose. Okay, so this is a desktop processor. Okay, the size is quite bigger. Okay, 32 or 64 bits used as an embedded controller. Okay, example here is x86. Okay, so this is a example of the general purpose processors. Okay, and this is what we call here the example of embedded processor application. Okay, by using the embedded processor, okay, you can use it as a digital signal processor, or sometimes we call it as a DSP. So this is a DSP by using the TMS3020. Okay, so this DSP is used to optimize for digital signal processing. So every time you're going to do a digital signal processing, okay, you need to have this board here. Okay, digital signal process board, which is have this chip TMS320. Okay, so this chip here is used to do the circuit, to amplify the signal, to what we call here, to do the filtering. Okay, and then to, okay, so anything regarding regarding the signal processing, okay, will be done inside of this processors here. Okay, then we have the graphic processor. So this is another applications, okay, by using the embedded processors, okay, which is this embedded processor can be used as a graphic processor. So this graphic processor is used to optimize for driving graphics display. Okay, so it will enhance your display. Okay, because it have an encoded programming inside there. Okay, to encode and decode the graphics. Okay, the videos. Okay, and etc. So example of a graphic processor is Radeon or GeForce. Okay, so I assume that all of you already heard of these things here. Okay, so every time you're going to buy the what we call it, the PC or laptop, okay, then you need to ask, okay, what type of a graphic processor inside of your laptop? Is it you have a GeForce or is it using a Radeon? Okay, so this is the examples of the graphic processors. And then we have the configuration application specific instruction processor or ASIP. Okay, sometimes we call it as a ASIP. So this instruction set tailored to specific application or application domains. Okay, and then you can customize it. Okay, so this ASIP can do some customization. Okay, depending on your if you're going to customize the power or the areas and etc. Okay, and this is an advantage lah. And the disadvantage is it has a higher non-return, okay, NRE and higher time to markets. Okay, example of ASLP is Extensa and ARC. Okay, so this is the application, okay, for the embedded processors. Okay, then we look at the second processors, okay. The second processor type, we call it as a FPGA. So FPGA is stand for Field Programmable Gate Array. Okay, so this FPGA is a hardware circuit that a user can program, okay, to carry out one or more logical operation. Okay, you can program this FPGA, okay, which is, okay, you can see here, you can reconfigure the logic, okay, you can program and reprogram back the logics, okay. So okay, with a standard chip, okay, such as an Arduino or a CPU in your laptop, okay, the chip is fully baked. Okay, means that you cannot reprogram your Arduino or your CPU. Okay, it okay, you will get what you get. But with this FPGA, okay, user can write a software that loads onto the chip and execute function. That software can later be replaced or deleted, but the hardware chips remain unchanged. Okay, so this FPGA, okay, instructions are executed parallelly. Okay, it acts as a hardware accelerator in hardware and software co-designed due to specific application it is programmed for. Okay, so processor architecture can be chosen according to available ISA tools. Okay, so different in deep submicron technology, number of port, memory, size. Okay, so depending on the ISA tool, you can reconfigure your FPGA accordingly. Okay, if you're going to increase the memory size, okay, so you can reprogram inside here. Okay, or decrease the memory size, you can reprogram here. Compared to Arduino or CPU, okay, once you buy the Arduino with 2K memories, okay, then you cannot increase the number of that memories. Okay, there is the difference between the FPGA as well as the standard chip that you can buy outside. Okay, and this the ni lah. Okay, so this is the chip for the FPGA. Okay, so this FPGA will not have the performance of a hardcore or a discrete solution. Okay, in many embedded applications, high performance is not required, and performance can be traded for the expanded functionality and flexibility. Okay, so FPGA is not so powerful. Okay, the performance is not so powerful, but you can expand the functionality and flexibility accordingly. Okay, so this is an examples of the FPGA. Okay, so the first one here by using the microblade. Okay, it has a 32-bit RISC, and the platform that you're going to use is a D-Link. Okay, then we have a NIOS. Okay, so it also have a 32-bit RISC and a platform. Okay, you're going to use the Altera platform. Okay, and then we have the Leon. Okay, so this one here using the Spark architecture, and it is an open software, and then you need to use the open platform, and then for the open RIC 1000. Okay, so this is a architecture by using open source architecture. So platform, you need to use an open platform, and last but not least is open source ARM7. Okay, so the architecture is by using the ARM architecture. Okay, and now it's already been shut down by ARM lawyers. Okay, so this is examples of FPGA. Okay, and then moving on to the next slide. Okay, we have another processor called a system on chip, or sometimes we call it as a SOC. Okay, now we are going to look at what is a SOC, or system on chip. Okay, the SOC actually is a microchip. Okay, you can see here it's very small, with all necessary electronic circuits and parts for a given system. Okay, so all of the parts in a one system already been embedded inside of this chip. Okay, contohnya smartphone or wearable computers. Okay, so all of the parts needed, okay, for your wearables computer, contoh you have a wearables jumps, okay, already been embedded inside of this tiny small chips. Okay, we have, let's put this another examples. Okay, if for example, okay, we have a system on chip for a sound detecting device. Okay, you're going to detect a sound. Okay, detect a sound. Okay, so inside of this chip here, okay, inside of this chip, okay, you may have the what we call here audio receiver. Okay, okay, which is this audio receiver is used to receive the sound, and then you have the ADC, analog to digital converter, which is to convert the analog signal from this audio that you are that receive from audio receiver to a digital. And then inside here it also have the microprocessor, okay, which is used to do the tool, okay, inside of the primary microprocessor. So all the processing part will be done inside of these things here. Okay, and sometimes, okay, you will have the digital signal processor inside it, DSP, okay, which is you can use to filter, do the processing to amplify the signals. And then after that, inside of this chip here, also it have a memories, okay, which is you can store all the sound, okay, that you retrieve from this what we call here, this circuit here, okay, and this audio receiver circuit, and then is the input output, okay, the GPIO, okay, which is used to, okay, as a input and output ports lah. Okay, so all of these things here is already embedded inside of this chip. Okay, previously, okay, in the embedded system, okay, you have the micro P, and then after that, you need to have another chip to do the audio receivers, and then you need to have another chip for the ADC and etc. But for the system on chip, all of this, what we call here, PI, IP, okay, all of these things here components already been embedded inside of this single ICs. Okay, so that's why we call it as a system on chip, okay, which is a complex IC that integrates the major functional element of a complete end product into a single chip or chipset consisting of an analog and interface circuitry. Okay, so these are examples. Okay, you can see here, these are examples of Intel Curie. Okay, it's a system on chip. Okay, the size of this SOC here, okay, processor here is the size of shirt button, but inside here it includes everything required to provide to compute power for the wearable device, okay, such as, okay, it has a 6-axis combo accelerometer, okay, it has an accelerometer inside here. It also have a gyroscope inside here, which is used to enable the movement tracking and gesture recognition. Okay, so this is the Intel Curie system on chips. Okay, the size is very small, okay, which is a size of your shirt button. Okay, for the current system of chip, okay, the current state of the art in the embedded system design is to have multiple computational and data processing engines, memory, and peripheral all constructed on a single chip. Okay, so we call it as a SOC. Okay, you can see here, all of these things here will be embedded inside of this one chip. So it's common for design to feature multiple general purpose central processing unit, which is a CPU, as well as special purpose digital processor cores inside of the chip. Okay, you can see here, inside of this chip, you not only have the CPUs, okay, you also have the DSP, okay, digital signal processor, and then maybe you have the temperature sensors, CMOS camera sensor also inside of this chip, okay, DMA control, speech codec, modulator, etc. So this is what we call as a system on chip. Okay, all of the module or components, okay, instead of the CPU, you have another processor already embedded inside of the same chips. Okay, that is what we call as a system on chips. Okay, so this is a we are going to look at the system on the difference between the SOC and system on board. Okay, so you can see here previously, okay, for the phones, okay, all of this phone here, all of the components, okay, that needs by this phone here, okay, is been embedded in the different chip. Okay, so you have the CPUs, contoh kat sini, and then after that, maybe you have the digital signal processing here, audio receivers, cameras, etc. All is not inside of the same chip. Okay, but now today what happened here is all of these things here seperti memory, interface, peripheral, DSP core, okay, and RF and IF substation all already embedded inside of single chips. Okay, so nowadays, sorry, most of the smartphone are using SoC. Okay, your smartphone now comes using the SoC. Okay, they are using a Qualcomm and MediaTek SoC. Okay, if you're using the iPhone, maybe it's using the Apple Biotech, if not mistaken. Right? So inside an SoC, okay, so what is inside of SoC? Okay, so this is a typical things lah. Okay, component that are inside of the system on chip. Okay, you maybe have one of several cores of embedded processor. Okay, maybe you have one core processor inside there, or you can have two core processor inside of the same chip. Okay, and then you have the specialized function unit. Okay, then you have the specialized function unit such as ADCs, pathway modulation, UART, and etc. inside of the same chips. Okay, core processor or accelerator also you can put inside the same chip. Okay, GPU, okay, or DSP processor. Okay, you can put the DSP inside here. Okay, if you're going to do the signal processing, or GPU if you're going to do a image processing. Okay, or graphical processing. Okay, so you can put it inside of this chip here. And then memory, of course, you need to put a memory. Okay, bus-based architecture, peripheral interface, okay, such as maybe you have the timers, DSC, LCD drive, okay, and then, okay, so you can put any protocols here as well inside of the same chip, depending on the system that you're going to use. And then after that, you will have the I/O channel. So all of these things here, okay, this is the typical things that the SOC has. Okay, so this is the SOC overview. Okay, since this is a system on chip, okay, you can see here inside of the system on chip SOC, you have the processors, memory controllers, okay, and then you have these peripherals such as the SPI, UART, I2S, I2C, USB, okay, interrupt controller, timer, etc. Okay, so what system on one IC. Okay, because we have the technologies. Okay, we can put everything inside of single. Gates. Okay, and it has a lower power consumption. Okay, and faster overall circuit and system operation. Yeah, of course. They what component inside of the single IC, and it has a smaller physical size. Okay, so the size is more board with microprocessor, embedded processors, and more real seat of all system on chips. Okay, so the of architecture that specify a set of architecture in of okay, so it will complex this and a lot of library for this this okay, okay, have so to get companies to of 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 this piece. So time to find from all object is your uh, you say you can làm some màu đi đi lại đi 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 tại đi tại block is that it is have the okay for and to use change as of the and have is there any tôi cái chuyện